Right. Because of that, tangent is sine over cosine will be negative. Cotangent will be negative. Secant will be negative. And cosecant will be positive. Good. Which of these five I already have, and I don't have to do anything? Yes, I have cosecant because it's 1 over sine, so this must be 4. Now, all I have to determine is cosine, because once I have cosine, then I have the other 3. So how do I determine cosine? You can use the triangle, or you can say cosine x equals negative the square root of 1 minus sine squared x. This is one of the most important results that we've learned in trig. Yes, the fact that you use a triangle is perfect. There is nothing wrong with it. But this is very useful for the next chapter, chapter 7. This is crucial, right? So then cosine x equals negative the square root of 1 minus 1/4 squared, 1 minus 1 over 16. And then I have negative the square root of 15 over 4. So, or you determine, as Chris did, and I think Shane just did the same thing, determine the other leg, which is fine. So then I know that cosine is the square root of 15 divided by 4. Then tangent will be this over this. So it will be 1 over the square root of 15. But I have to rationalize it. And you did. The square root of 15 over 15. Don't forget the minus. I'm squeezing it in there. Then cotangent is this one reversed. And then secant is this one reversed. So 4 divided by the square root of 15, which is negative 4, the square root of 15 over 15. Right. So, but yes, using a triangle and positioning it in the second quadrant is fine. It's fine. Okay? Good. So let's continue. Any questions for me? Any questions? Okay. Is there anything else from section 6.1 through 6.3, or can we continue with 6. I cannot continue with 6.4. I have to go back to chapter 5. So let's go back to the syllabus just to show you where we are and what we did. I'm hoping you're going to look at 5.1 and 5.2. They are very similar to the problems we did in 6.1, 6.2, and 6.3. But please look at these problems. Just try a few as a review, okay? Please. You don't have to turn this in if you don't want to. But it's useful because it will just refresh your memory on the topics we discussed. Now, I'm trying to get to 6.4, but before I get to 6.4, unfortunately, I have to look at these 3. Okay? So I have to look at 5.3, 5.4, 5.5, and then I can come back to 6.4. Okay?
Is 5.3, 4, 5.3, 5.4, 5.5 new stuff, or is it just like?
Yes. Yes, these are required. These are required.
Okay.
Yes. These are required problems. I'm going to go over all of them. Not all of them, all different types. So you have an example, at least one. But yes, these are required. 5.1 and 5.2 are basically in 6.1 and 6.1 and 6.2. But I still want you to look at those. But these are not. This is new material. Okay. So let's go back to 5.3. We're looking at trigonometric graphs. All of them, actually. 5.3 and 5.4 and 5.5. They all deal with graphs. So 5.3, trigonometric graphs. We are going to look mainly at 3 different functions. And you can say, why am I skipping the other 3? I'm happy if you remember or add, and also add to your list of different functions. Like we know a lot of functions. Let me just review a few. Linear, quadratic, cubic, 4th degree, absolute value, radical, rational, right? And now we're going to look at 3 more graphs, 3 more functions. Sine, cosine, and tangent. Now, what happens to cotangent secant and cosecant. So if you look at the graphing calculator for a second, I'm not saying that these three graphs, secant, cosecant, and cotangent, are not useful. They're very useful. However, see, once we understand and we are able to play and graph sine, cosine, and tangent, we will have no difficulties in graphing the other ones. Okay? But look at what it's written under on the same key, basically, with the second key. What is that? What do you think sin and the power -1 means? Exactly. The same thing here, cosine inverse. And the same here, tangent inverse. So you do not see cotangent, you do not see secant, you do not see cosecant. It doesn't mean that they're not important. It doesn't mean that they don't show up in real life situations. But they have a little bit less applicability in comparison to sine, cosine, and tangent. Okay? So how will you graph, for example, cotangent? There is no button for cotangent. But you remember that cotangent is 1 over tangent, or cosine over sine, and you make it up, right? You will put it in the graphing calculator. How? So you'll put in the graphing calculator as cosine x divided by sine x. And that will be your cotangent, and you'll be able to graph it. How will you graph secant if you need to? There is no button that says secant on it. 1 over, if it starts with s, it has to be the other one. Cosine. How will you graph cosecant? 1 over sine. So that's why I would like to focus on 3 most useful and mostly applied functions, more common than any other function. The other 3, I would say, sine, cosine, and tangent. Good. So let's start with sine. So f of x equals sine x. Number 1, I'd like to mention the fact that it has a very important property. It's a periodic function. So what does it mean? Periodic function. Here it is. So let's suppose I have, here's assuming I have the graph here, graph of sine, complete graph, complete rotation, everything complete. Then it will repeat, and then it will repeat, and then it will repeat on both sides in blocks. So that's the meaning of a periodic function. It will repeat indefinitely. Okay. The period is 2 pi for sine. Remember, we looked at odd and even functions. Can anyone refresh our memory? Which of the 6 trig functions is odd? Sine and cosecant. All trig functions that have sine in them would be odd. And which functions are even? That's it. Cosine and secant. Okay, so let's also, since I'm here, and I would like to have a table for this, the period for these functions. There are 2 options only, 2 pi or pi. Only 2 functions have period pi, tangent and cotangent. Everything else has a period of 2 pi. What does that mean? They repeat in blocks of 2 pi, not in blocks of pi. So sine, cosine, secant, and cosecant. So all trig functions except tangent and cotangent have a period of pi. Have a period of 2 pi. Tangent and cotangent have a period of pi. Good. So we will look at a complete rotation. We will graph this function, which is sine x, on a complete rotation between 0 and 2 pi. So let's take a look. What is the maximum value that sine can have?
1.
Exactly. What is the minimum value that sine can have? Exactly. Remember, at pi over 2, sine is 1. At 3 pi over 2, sine is -1. So everything happens for sine between +1 and -1, except, what if I have this? We will get to that. Don't even write it. I'm just discussing it right now because I want to refresh your memory. How high will this graph go?
Isn't it shrinking?
Am I changing what? Am I changing x or y? Does it touch x? Does the 3? No. So how high will that function go? Exactly. How low would this function go? Exactly. Absolutely. So we'll talk about this. We'll look at transformations in a minute. So this is not important at this point. But is that clear? Okay. So let's go around the unit circle. So I'm going to say, see, in order to keep a uniform unit, I have here pi over 2. I have here pi. I have here 3 pi over 2, and I have here 2 pi. And notice that I try to make them as equal as possible. Of course it's not, I can't be perfect. So, okay, so now this is a pi over 2 unit. Pi over 2 unit is pi divided by 2. So this is about 1.6. So this is about 1.6. This, where's my, right? Okay, so this is about 1.6. So 1 here cannot be at 1.6. So if this is basically 1.6, this is 1.6, so 1 should be about here, right? So this is my 1, and this is my -1, assuming I want to keep the same. Okay, very good. So this is y. Let's go around the unit circle. I'm at 0 radians. 0 radians, what is the value of sine 0? Very good. I got to pi over 2. What is sine pi over 2? Very good. I got to pi. How much is sine pi? Okay, perfect. I got to 3 pi over 2. And finally I got to 2 pi. Ready? Okay, so the first thing, so this is the function f of x. I have to write sine x. Number 2 on our list. The first one was period. And can I continue? Yes. Very good. We're going to get to that in a second. Okay, so it is clear that this function continues forever. Its domain is all real numbers, right? So I'm going to say domain. Everything. And remember what we said. How did we define sine? As the opposite over the hypotenuse. How can I have 3 pi, 2 pi, 4 pi? How can I have a sine of 4 pi? 4 pi doesn't fit in a right triangle. Because it's the reference angle that I'm determining sine of 4 pi with. I'm not putting 4 pi, which is 720 degrees, in a right triangle. No, I'm determining the reference angle, and I'm determining the sine of the reference angle, which is always an acute angle between 0 and 90. Okay, so domain is everything. Number 3, something that is called amplitude. The amplitude is the difference between the maximum and the minimum divided by 2. Or I should say the distance between maximum and minimum divided by 2. So let's come back. What is the distance between -1 and 1? How many units between -1 and 1? 2. Divide that by 2. The amplitude is always the number in front of sine. So if I have f of x equals 3 sine x, the amplitude will be the absolute value of 3. The amplitude is always a positive number. Remember, you already told me that this function will go as high as 3, will go as low as -3. What is the distance between -3 and 3? 6, and divide that by 2? 3. So the amplitude is 3. Okay. There is also something called phase shift. So coming back to our function, what is the amplitude for this? I would like to write the, oops, I didn't mean that, to put the absolute value around A. I have to put the absolute value around what you give me. So what would be the amplitude for the original base function? Yes, will be the absolute value of 1. So keep that in mind. The amplitude has to be a positive number. And you can say, but it's redundant to put the absolute value on 1. True. I'm just reminding you that it's always the absolute value. Okay. Now on our function, back to our function, f of x equals sine x. The phase shift is basically a horizontal shift, either to the left or to the right. It's called phase shift for trig functions. But it's the same shift that we had before with, for example, when we had x plus 1 squared. What was the horizontal shift for this function? Careful. Is it a transformation on x, or is it a transformation on y? If it's a transformation on x, is this. If it's a transformation on y, is this. Which one is it? On x. Where does it go? Left one, exactly. Okay. So is there a transformation on x here? No. So I will say the phase shift, and the notation is lowercase b. For our case, the phase shift is 0. So let's say if I want to look at the function, we're going to graph these two functions. Give me a phase shift to the left. Yes, so if you wanted to, yes. Plus, but let's make it into an angle. Let's say pi over 6. So how much is the phase shift in this case? Because I would like to emphasize that. Where does this graph go? Exactly. When you say left pi over 6, it means negative pi over 6. So let's graph these functions. If you have your calculators, if not, you can use mine. So let's graph them. So let's graph, first of all, sine x. Sine x. Let's go to the mode. I have it in radians. I want to keep it in radians for now. And get out of there. Go back to y equals. And now I want to create my own viewing window. I don't want to see the whole thing. I would like to see it's giving me the whole thing already, the software here on the computer. But I don't want to see the whole thing. I want to see one complete period. So I go back to the viewing window. How high do I want the graph to show on the viewing window? And how low? Yes, I would say between -2 and 2, yes, absolutely. So -2 and 2 for the y-axis with a scale of 1 is okay. But what about the leftmost point for x? Because I only want to see one complete period. 0. And then how much to the right should it go? Yes, I have to write 2 times pi. And I want a scale that I used in the graph. What was the scale for us in the graph on paper? Exactly. I want pi over 2. Pi divided by 2. Oh, that's not what I wanted. Pi divided by 2. Okay? So now when I hit enter, I'm going to see just one complete rotation, or if you want one complete period for sine. It's very clear that it does not go beyond 1. It's very clear it does not go below -1. Now I would like to graph the other one that we said has a phase shift of -pi/6 to the left. But I have to adjust my viewing window, right? I have to include a little piece on the left. Because if I don't, if I just go back blindly and put the second function in there as sine, and in parentheses, x plus pi divided by 6, and hit enter, I will not see a little piece of the next function because it's shifted to the left 30 degrees, or pi/6. Is that clear? So it goes to the left, so I don't see this little piece here. So that's why I have to adjust the viewing window and start at -pi/6. So let's go to the viewing window, and I just change the x value to the starting point to -pi/6, and then hit enter. And if I do that, I will see a little bit more of sine, right? But I will see a complete period for the other function. Of course, it's not going to end here because I didn't cut it off here. It will continue. So this is 30 degrees of pi/6. Of course, here's the same, and here's the same. So that shows a left shift of -pi/6. So the graph starts at -pi/6. So now here's a question for you. Can anyone give us, for f of x equals sine x, the most useful interval in which, sorry. So can anyone for sine x give us the most useful interval that will show a complete period for this function? Excellent. Can anyone give us a complete, the best interval for this function?
pi/6.
Yes?
2pi.
-pi/6. Very good. Comma. Let me give you the answer here. B plus the period.
So b is pi.
No, B is not pi/6, but P is. Exactly. And add 2 pi to it. Pencil and paper. So -pi/6 plus 2 pi, and tell me what to write in there. Minus.
So 11 pi/6.
Exactly. So the most important interval for all these functions, sine and cosine, will be B and B plus the period. Whatever that is. B could be positive or negative. Now here's a crucial question for you. Let's say I have f of x equals -2 sine 1/2 x. I want a few things. Number 1, period. Number 2, I want amplitude. Number 3, I want interval. I should have put phase shift, I'm sorry, first. So I'm going to do 3b and 3a. And we have to start with 3a, phase shift. Okay? So let's analyze. Let's start with the amplitude. What will the amplitude be? the absolute value of
Optimal one.
the absolute value of -2, which is 2, right? Because remember, this number can be maximum 1, minimum -1.
Oh, it's a.
Multiply by -2 will be maximum negative, still maximum 2 and a minimum -2. Is that clear?
Mhm.
Perfect. Now let's clarify the phase shift. What is the phase shift for this function? Exactly. We're not adding or subtracting anything from x. Exactly, 0. It doesn't go left or right. Perfect, excellent. Okay, now I'd like to talk about the period. And do not say anything because I need to refresh your memory on something. How many transformations we looked at? We looked at shift, horizontal shift, left and right. We looked at vertical shift, up and down, right? Clear, no problem. We looked at, that's one, shifts, right? Second one, stretching, right? So we said if this is x squared, twice x squared, will it be this or will it be this? The first one, it's a vertical stretch if the number in front is 2, more than 1, right? Okay, what about 1/3 x squared? This is x squared, 1/3 x squared will be this. Excellent. That was a vertical stretching and shrinking. Now I would like to talk, and the other one was reflections. I don't need it right now. Okay, we'll talk about it. This has a reflection as well. But now I'd like to talk about this one. When we change x into 1/2 x, what did we say? Does it do this or this? Right. So when we multiply by 1/2, although we expect this to be the case, it's the opposite. Excellent. It does this. So then, now I'm asking you, I couldn't illustrate with this function when we talked about it because we didn't know trig functions then. So if the period of sine x is 0 to 2 pi or 2 pi, what would be the period of 1/2 x, sine of 1/2 x, based on what you just told me? Exactly. We'll check in a minute. So the period is always 2 pi divided by the number that multiplies x. That's the reason why we get 4 pi. Very good. Exactly. So now I'm asking you to give me the most important interval. And let me refresh your memory. It's b plus the period. So what will be the most important interval for this function? That will give us the whole thing. Yes? Exactly. So let's take a look. Now this would have been a very useful function to illustrate the horizontal stretching or shrinking, but we didn't have it available then. So that's why I couldn't make use of it. So let's go back. Clear everything. And let's put in -2 sine. I don't want to put a negative yet because I want to discuss it for a second, right? Okay, I just want to compare sine x to sine, because I want to talk about that -2 in front. Sine 0.5x. And now, of course, I have to change the viewing window. So 0 is okay. 2 pi is not okay anymore. So I have to go to 4 pi. And the scale can stay. I don't mind. Also, how high should it go? Let's keep it because we did not include that -2. We're still discussing the graphs. Okay. So here's sine x. In 0 to 4 pi, how many complete periods will I have? Or complete rotations, or if you want. 2. That's exactly what I have. So here's sine between 0 and 2 pi, and between 2 pi and 4 pi. And look at sine 1/2 x. It has a complete period between 0 and 4 pi. Why? Because that 1/2 does this. What if now I want to graph a function, let's say f of x equals sine 3x? Right, by a factor of 1/3. So what will be the period for this now? Exactly. Exactly. So 2 pi divided by 3. So between 0 and 2 pi, how many complete periods of this function will I have? And between 0 and 4 pi, how many will I have? 6. Let's take a look. Let's go to y equals. So the third function will appear in a different color, and I have sine 3x. Here it's come. Here it is. 1, 2, 3, 4, 5, 6. Only because x was multiplied by 3. So when x is multiplied by 3, when x is multiplied by 1/2, which we knew from chapter 2, but we could not illustrate with these the trig functions. Okay, finally, let's finalize this and look at examples. Now let's put in there the 2. So now let's talk about this 2, sine 1/2 x. So it's the same graph of sine 1/2 x, but this graph will be what? Yes, in a second we'll put the negative.
It'd be taller.
It will be stretched. So this graph will go how high? 2 and -2. Okay. And now if I put the minus in front, because I want to show this in 2 steps. So first of all, this graph will do this, and then
It'll start from the bottom.
exactly. So I want to focus on these 3 graphs. This, then the one with 2 in front, and then the one with negative in front. So I'm going to go back and remove. What am I removing? I'm removing the last one. I'm removing the first one because I want 2 sine 0.5x. And then the last one I want with minus 2 sine 0.5x. Oops, I didn't mean that. Okay, ready? So blue, red, and black. Ready? We still have 0 to 4 pi, because I have to. For which one? For which one? Well, for all of them, right? Good. So let's graph. So that's the blue. Right, the 2. Here it is, the sine 0.5x. And now the negative sine 0.5, 2 sine 0.5x. Okay, so one more time. This is 2 sine 0.5x. This is sine 0.5x. And this is negative 2 sine 0.5x. Is that clear? Okay, perfect. Good. So I'd like to look at a couple of examples now. On page 396, pages 396, 397. Let me look at my time here. Oh, I'm still okay. Perfect. Okay, and then we'll look at cosine and tangent. But right now, let's just choose sine. A couple of examples with sine. Find the amplitude, period, phase shift of the function, and graph one complete period. So let's start with that. If you want, find the amplitude and period of the function and sketch its graph, and graph the function. They're all the same, 1 through 41. So let's choose.
36.
We want to look at 36. So we have y equals 2 sine 2/3 x minus pi over 6. This has a lot, right? Good. So I'm going to start with period. Oh, let's just list them. B, phase shift, 3, interval, and 4, amplitude. And then the graph. So I would suggest let's start with the amplitude. Can anyone give us the amplitude? Right. The amplitude is the absolute value of 2, which is 2, which means this function will go to the highest point of being
2.
and the lowest point of being for the y value. Good. Very good. So now this function needs a little bit of work. It is true that this is the number that multiplies x. It is true that the period will be 2 pi divided by that number. I have 2 pi over 1 for the top times 3 divided by 2 for the bottom, because I have to multiply by the multiplicative inverse. I will simplify, and I get that the period of this function is 3 pi. But now the function needs work for identifying b. Nope. I have to factor out 2/3 in front of the parentheses. I cannot take 2/3 in front of sine. That will never be allowed. But I have to take this parentheses, like 2/3 x minus pi over 6, and I have to factor out 2/3. If I don't factor out 2/3, I will not be able to identify the phase shift.
X by itself.
Yes, exactly. Because remember, a shift left or right is something that is added or subtracted to x only. So I have x minus. How do I get this number? Well, from pi over 6, to pi over 6, I divide pi over 6 by 2/3. That's all I have to do. So then I have pi over 6 multiplied by 3 over 2. I will simplify, and I get pi over 4. Now let's say you don't believe this. Assuming you don't, let's imagine that we distribute 2/3 back in there. 2/3 times x is that 2/3 x. 2 over 3 times pi over 4, I simplify 2 and 4 by 2, and I get pi over 2 times 3 is pi over 6. So the function y, which was 2 sine 2/3 x minus pi over 6, can be rewritten as 2 sine 2/3 x minus pi over 4. Only now I can identify the phase shift. What is the phase shift? Yes. And it's positive, and the shift will be to the left or to the right.
Correct.
Exactly. And now I'm ready to identify the interval, which I know is b, and b plus the period. Pi over 4 indeed, comma. Yes, I have to add 3 pi to pi over 4, so it's 12 plus 1, 13 pi over 4. Are we okay with this? Say it again.
We have pi over 4 and then put it over the number of times multiplied by x, which is, or what you saw was.
This is how we factored, if you remember the beginning of the semester when we factored from those handouts.
You
go back up for a second?
Sure.
Yeah.
You mean this one?
Yeah.
So it's b plus p. So pi over 4 plus 3 pi, that's 12 plus 1, 13 pi. So if I choose my unit to be pi over 4, please follow this for a second. If I choose my unit to be pi over 4, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1, 2, 3. 13 pi over 4 and pi over 4. Right in the middle, I will have, so the function will do this. It will go up to, if assuming that this is 2 and this is negative 2, right in the middle it will cross, right? Here it is. This is the graph of 2. Sine 2/3 x minus pi over 6. Let's show a complete graph. Ready? So let's plug it in, delete, you can clear everything. Okay, so it's 2 sine 2 over 3. Be careful how you put it in. I will put parentheses 2 divided by 3 times x and minus pi over 6. I always do that. What did I do now? So 2, bless you, sine, parentheses 2 divided by 3, close the parentheses, x minus pi divided by 6, close the parentheses. Okay, now I have to go to the viewing window. So the leftmost point for us will be pi divided by 4. Then the rightmost point will be what? Exactly. 13 pi over 4. Good. And then the scale, okay, let's choose pi over 4. And y minimum or y maximum can stay, but I like to use -3 and 3 so it doesn't hit the edge of the graph, of the viewing window, it doesn't matter. And now I'm ready to graph it. I have to see a complete period. Very good graph, very good function it shows. It's a very good example. So I know that this is pi over 4, it goes up to 2, it crosses right in the middle, and it comes back at the end at 13 pi over 4, which we already had on paper. Any questions? Any questions about sine x? Okay. Any questions about transformations on sine x? Any questions on sine x?
Yeah, I did have one real fast. So for the phase shift, I would say with pi over 4, correct? And then just the general defined phase shift is the number of times multiplied by x.
The phase shift?
Yeah.
So when you factor out something, you're dividing that by that in front. So if you have something like x to the 4th minus x squared, and you write x squared minus 1, this is what you do. You divide x to the 4th by x squared to get x squared. You divide x squared by x squared to get 1.
Right.
So if I have 2/3 x minus pi over 6, and I want to factor out 2/3, you divide this by this, and you get negative pi over 4, like exactly what we did with this. So you're dividing pi over 6 by 2 over 3 to get pi over 4. You can always take a moment and put it back in. This times this is this, and 2 over 3 times pi over 4 is pi over 6. To double check. Is that better?
Yeah, so,
Was that your question?
yeah, so I was kind of saying, so for the interval, the
Yes.
general.
Oh, for the interval, yes.
Well, I'm just saying, so like for the interval, it's B and then comma B plus P.
Yes.
And I was just saying, is there something like that for phase shift, just as
If there is no
like
phase shift, there is 0.
Okay.
But this one was a phase shift of positive pi over 4. That's why we had to start at pi over 4 and move 4 pi to the right. Is that okay?
Yeah.
Okay, so now let's go back for a second, because I want to mention something. When we first talked about sine, and we first graphed it, and I said this is complete, but it goes on forever. So this is 0 to 2 pi, but it goes on forever on both sides. Okay, now the question is, and Shane already said that. He said, oh, now I see why sine is odd. Because, as you see, if I draw a line between 2 points on each side of the origin, going through the origin, like here, like this. Let me use it blue. So if I draw, these two pieces are equal. It's like for x cubed. So that's why we know that this is an odd function. Perfect. Okay, now here's a question for you. Looking at this graph one more time. And a minute ago, I showed you on the graphing calculator. And I said, look, here is sine. And then I said, look, in my calculator in blue, what do you see? Right. But now let's look at this graph again. What is the property of a property has a function to have in order to have an inverse function? Right. But is this function one-to-one? Don't say anything. I'm going to cross it with a horizontal line. Is this function one-to-one? What does one-to-one mean?
One x value and one y value.
That's for a function. But for a function to be one-to-one, every y value has to have only one x. So the vertical line test tells us whether the graph represents a function. The horizontal line test shows us whether the function is or is not one-to-one. Is x squared one-to-one? No. What did we do?
We only found one side of it.
We say we truncated the domain. We minimize the domain so that we make it one-to-one. We're going to have to do the same thing here. This is not one-to-one.
So is that why we only found the interval?
Yes. So what I'm saying is, what my next step is, I would like to graph the inverse. Okay? So, but first, in order to find, even talk about this, by the way, we have two notations for sine inverse. We have sine that looks like it's a power -1. We know that this is sine inverse, the inverse function of sine. But we also have another notation, which I personally prefer when I type, because I don't have to use the power. It's easier. Arc sine. You don't have to use arc sine, but I may use it in a test or a quiz because it's easier for me to type.
It's the same thing.
It's the same thing. We have two notations for the same thing. Good. So now, because we want to define this function, here's what we're going to do. We're going to say, which is false, it's not true. We're going to say that sine is not defined on all real numbers. We know it is, right? It exists everywhere. There's no restrictions whatsoever. But instead, we're going to say that it's only defined between -π/2 and π/2. If we do that, will this piece alone be one-to-one? Yes. That's the reason why. Okay? So we're going to say that sine inverse, I'm sorry, I'm talking about sine. I didn't get to sine inverse yet. I don't know why I wrote that power. So sine is defined on the interval. Can anyone give us the interval again? Very good. Because we have to show every point, every value. That's why we have to use negative pi over 2. Pi over 2. And what will be its range? Of course. Negative 1, 1. And now I'm ready to define sine inverse because this piece is 1 to 1. Now please tell me what will be the domain of sine inverse and what will be the range. You can say you haven't even talked about the function. You haven't even shown us the function. True. But I can still find its domain and range. How do we define the domain and range for an inverse function? Where do they come from? Okay, so let's go back to this. Sine negative pi over 2 pi over 2 negative 1 1. Of course. Of course, that's why it's called the inverse function. We'll do the inverse. We'll bring those numbers back to angles. So allow me to stop this because